We're going to take a look at logarithmic functions, and a logarithm is just an exponent. And so just like exponential functions, logarithmic functions have a lot of applications. For instance, the spacing on the frets of a guitar can be represented by a logarithmic function. Okay, so that's just one example. There's all kinds of examples, but we need to make sure we understand some definitions. So again, a logarithm is just an exponent, and this was our exponential function, and its inverse is also a function. And remember, an inverse is just where you switch the x and y values. Okay, so this logarithmic function can be written in this form right here. Now this is read y equals log base b of x. Now in the long run we're going to use logarithms to solve exponential functions. Exponential equations. And you're going to be wanting to switch back and forth between these two forms when you're doing that. And it looks kind of scary, I guess, but it's, if you're reading it correctly, it's not that big a deal. This is x equals the base b raised to the y power. Log base b, so the bases are the same, of x. So again, y is an exponent, so when we use it to solve for an exponent, the exponent will come out equaling log base, whatever the base is, b of x. So for the purposes of the graphs, I'm going to use log base 2. And you usually don't use log base 2. It's usually log base 10. You can use log base 2, but it's just kind of standard to use log base 10 or log base e, which is a natural log, and we'll get to that later. But the graphs are a lot more defined when we're using a base of 2. Okay, so these two functions are inverses of each other. Okay, and just like any other inverse, that means when you graph them, they would reflect across the line y equals x, and you see that they do. Now some things are different. If you remember, we talked about for the function 2 raised to the x, a normal exponential function, our domain was all reals. Okay, but this is going to switch for a logarithm. Actually the range in this case is all reals. And instead of having an asymptote at the x-axis, we have an asymptote on the y-axis. And for the exponential functions, if we didn't, the basic exponential functions, if we didn't add or subtract anything to them, they always went through the coordinate 0, 1. Well, that's kind of similar for logarithmic functions. As long as we're not adding or subtracting anything to them, they're going to all go through the point 1, 0. Okay, so these are just reflections of each other because of the fact that they're inverses. So we're just going to move this graph of log base 2 of x around just to show that any function kind of has these similar properties to it. This blue curve is our standard log base 2 of x. Okay? If you want to multiply that function by a -1, it reflects over the x-axis, just like any other function. And again, that's because if you have a positive value from this one and then multiplied by a negative, it would give you a negative value. Okay, and so that would be all these. And vice versa, if you had a negative value out of this one down here, if you multiply that by a -1, it would produce a positive value. Again, the blue curve represents log base 2 of x, and just like any other function, if we add or subtract numbers to the outside, okay, and so we're not adding it in here with x, we'll do that later, it will move the graph, the curve, up or down. So this red one represents this function, log base 2 of x plus 3. And you notice that the graph of the red one is simply shifted up 1, 2, 3 spots. When we subtract a number, it'll move it down. And so this purple curve is represented, or represents the function log base 2 of x minus 5. And again, that's just going to shift it down 5. 1, 2, 3, 4, 5. On these curves, you notice that it is getting shifted or translated left and right from our original log base 2 of x. Okay? Again, when you're adding these numbers inside with the x value, okay, it is moving it left and right, but opposite of the sign, right? This red one, x minus 2, has shifted the curve 2 spots. X plus 4, 4 spots to the left. Now, of course, we can move them left and right and up and down at the same time. So, here's our basic curve again. And we're doing this too. We're adding 2 to the outside and subtracting 3 on the inside. So this is going to move it to the right 3 and up 2. And so let's pick this point, right? 1, 2, 3, up 1, 2. Okay, so all of these points are shifted over 1, 2, 3, up 1, 2. So now we've taken our basic log base 2 of x, we've reflected it over the x-axis, we've moved it to the left 1, and we've moved it down 4. Okay, so it's flipped, spun around, and gone to the left 1, down 1, 2, 3, 4. So here's a generic statement, okay, and whatever log, whatever the base is that you're looking at, the number inside the parentheses will move it left and right, and it will go in the opposite direction of this sign. And the number that you add or subtract to the outside will move it up and down in the same direction as this sign. And of course, if we threw a negative out front, that would reflect it over the x-axis.